In 2003, the world threw a party. The human genome, finished, read from cover to cover. Except it wasn't. 8% of the book was still blank. Whole chapters no one could read. The centromeres, the tips of the chromosomes, the parts that break in cancer. And that blank stayed blank for 19 more years. When we finally filled it in, the finished book turned out to belong to someone in particular. To read a genome, first you have to read a single letter. In 1977, a quiet Englishman named Fred Sanger found the way. Chop the strand into pieces, sort them by length, read the latter one rung at a time. He'd already won a Nobel Prize once for spelling out insulin, the first protein ever sequenced. Now he'd earn a second for teaching the world to read DNA. Only one person in history has ever won that prize in chemistry twice. It was him. His method was slow. It was hand done. And for 30 years, it was the only way there was. Reading one gene was a PhD. Reading all 3 billion letters was a moonshot. In 1990, the world took the shot. The Human Genome Project. 15 years, $3 billion, every nation pitching in. The man who launched it was James Watson, co-discoverer of the double helix itself. But almost at once, a fight broke out. Not over science, over ownership. The government wanted to patent raw gene fragments, thousands of them. Watson was furious. You cannot patent nature, he argued. In 1992, he quit rather than sign on. A young geneticist named Francis Collins took the wheel, and the public project sailed on. Slow, careful, mapping before it read. Then, in 1998, a challenger appeared. Craig Venter and a private company called Celera. His bet was speed. New machines had just arrived. Automated sequencers that ran DNA through hair-thin tubes, hundreds at a time. Celera bought 300 of them and read 1 billion letters a month. His method was reckless and brilliant. Blow the whole genome into random fragments and let the computers puzzle it back together. The public consortium mapped carefully. Celera sprinted. It became the most famous race in biology. It ended, on purpose, in a tie. June 2000, the White House, Collins and Venter shoulder to shoulder, announcing a draft. The finished papers came the next winter, back to back. The public team in one journal, Celera in another. 3 years later, in 2003, they called it done. 99% of the genes, spelled out letter by letter. And that was worth every dollar. But a genome is not only its genes. About 8% of it had never been read at all. Not because it didn't matter, because it couldn't be done. The missing 8% was the hardest terrain in the whole genome. The centromeres, the wastes of each chromosome, the anchors that let a cell divide without losing its place, the telomeres, capping the ends, long stretches copied and recopied, stacked like dunes in a desert. The machines read in short snippets. In a desert where every dune looks identical, a short snippet has no landmarks, no way to know where it came from. So the assemblers gave up on the deserts and left them white on the map. 8% of you unmapped. Meanwhile, sequencing got cheap, absurdly cheap. A new generation of machines read millions of tiny fragments in parallel. The price of a genome fell off a cliff, from billions of dollars toward 1,000. Suddenly, a genome could be read in a day for the cost of a laptop. But to go that cheap, these machines read in even shorter snippets. Great for the easy 92%, useless in the deserts. The cheaper we made it, the more stubborn the blank stayed. The answer wasn't a faster computer, it was a longer read. A different kind of machine arrived from companies called PacBio and Oxford Nanopore. Instead of snippets, they read DNA in long, continuous ribbons, Tens of thousands of letters in a single pass, long enough to carry a landmark on both ends, long enough to walk clear across a desert without ever losing your footing. For the first time, the blank could be read. Someone had to go and do it. 2022. A team with a fitting name, Telomere to Telomere, finished the map. 200 million letters no reference had ever contained. Nearly 2,000 new genes. The first gapless human genome. Every centromere and telomere resolved end to end. And the blank turned out to be anything but junk. The centromeres hold the machinery that lets a cell split its chromosomes evenly every time it divides. The short arms hold the clustered genes that build our ribosomes, the factories for every protein you make. Filling the deserts also corrected thousands of long-standing errors and made variants we have been misreading for years, even clinically important ones, finally legible. But it came with a quiet asterisk. To make the puzzle solvable, they used a very unusual cell, one that carries two identical copies of every chromosome. In effect, a single genome read twice, cleaner than any real person, and missing a Y chromosome entirely. That one was finished separately a year later. A flawless reference, but not a human being, because a human being is not one genome, it's two. You are diploid, two copies of every chromosome, one from your mother, one from your father. And they are not the same. They differ, letter by letter, millions of times over. That difference is where medicine lives. A recessive disease needs both copies broken. Often, it's two different faults, one on each copy, that only cause harm together. So the question that matters isn't just what variants you carry, it's which copy each one sits on. Answering that is called phasing, and for 20 years, a single genome reference could never quite do it. August 2026, the same team did it for real. Not a mole, not a composite, a living, consented donor, known to science as HG002. Both chromosome sets, both parents' copies, fully separated, fully phased, telomere to telomere. 900 million letters more than the best benchmark before it. 15% more genome laid bare. Led out of Johns Hopkins and the National Standards Lab, published all at once as a dozen papers, with the genomes of other animals alongside, from macaque to giraffe. For the first time, this was not a human genome. It was a whole human being, written out complete. For 20 years, reading your genome meant lining you up against one borrowed reference, mostly the DNA of a handful of strangers, and noting where you differed. But any two people differ at millions of letters, and some stretches of DNA that whole populations carry are simply missing from that one reference. Measure everyone against a single stranger, and you miss exactly what makes them different. That is why no one person can be the human genome. So science is building a pangenome, dozens of complete genomes, and climbing. So your DNA is read against people like you, not one borrowed map. And beyond that, the real prize, not the reference, yours. Every letter, both copies, yours alone. The first genome cost billions and took 13 years. Yours will cost a few $100s and take a couple of days. The book that was never finished is finally being written. A complete personal copy for each of us, one person at a time. 1977, the first letter. 2000, the draft. 2003, the desert's still blank. 2022, gapless at last. 2026, complete. And, for the first time, diploid. Half a century to learn to read ourselves, cover to cover. The Gene Channel.